and they'll bring Falcons in. And there's a weak point on Falcon jets, and they actually have a STC to weld on a bracket. So they'll TIG weld brackets on near the spar where they have found cracks over the last few years. Does Falcon know it? Yes. Does Falcon fix it? No. And so Duncan, which is large, they do corporate jets, probably about an hour south of here. That's kind of what they do. They'll put brackets on. So, FAA question says, why should an aircraft technician, maintenance technician, be familiar with weld nomenclature? Why? Why does it even matter? May I already listen to this question?
Yeah, so that it gave familiarity with welding techniques.
That is not. It's actually to accurately visual comparison or pictorial comparisons can be made. So you can look at them and say, yeah, that was good. No, that was bad. So you're going to be a critic or critiquer of something that maybe you don't even know how to do. Oh, wow. Yes, Joe?
I'm pretty sure that Prepware is currently saying number alpha is correct. Number alpha. Letter alpha. Option alpha. Sorry.
Yeah, that's interesting because that's not the right one. That must be a new update, but it's really so, and even this is in Verbata, if you're an AC 4313, AC 4313 page 421 will go into weld and brazing, okay? And so this is a engine mount, like off an A65 here, okay? One way you know, it's got these straight mounts instead of a dynafocal mount, okay? So very old, but it's got some serious welds right around here, okay? Good tubular weld. It's pretty common. That's all that will hold the engine on to the fuselage. Super light, hollow, very, very thin material that we use in aviation, okay? And that's predominantly, you know, if you look at tubular steel or 4130 chromolybendium or Plymouth steel, the ones that we use in aviation are extremely thin compared to like ones that they'll use for drag cars and stuff like that. So they'll have a good solid tube, but it will have a pretty thick wall. We have a very thin wall. When we say if you can weld in aviation, you can just about weld anything. Because it's like welding paper. So.
Does it have to be preheated?
No. No. Alrighty. So, materials processes, inspecting welds. As I said, it's on page 463. 463 is where we're actually at. For inspection purposes, 463 and AC 4313. All right, welding and brazing, okay? And this also goes back to inspection method. So what's the purpose of weld inspection? Is to be able to be familiar and look at the weld and say, yep, that's a good weld. Nope, that's a bad weld, okay? Inspecting an airworthy and unairworthy welds. AC 4313 requires a requirement for welds. I already mentioned that. Specifically at page 4-63. There we go. Here's a Husky. Husky. Fuselage frame. Okay. Big back. There we go. Nice little side view there. why should AMTs know weld nomenclature? So they can make an airworthy weld? No, so they can recognize an airworthy weld during inspection, correct. You're not a certified welder, but a certified inspector. Or a certified inspector of weld, once you get your A. So. Everybody understand that so far? Okay, how many of you have ever welded before? Okay, thank you. All right, how many of you have ever TIG welded? 2, 3, okay, 4. 4 welds, four TIG welders, okay? All right, so we have several different types of welds. You have a lap weld where one piece of material goes over the other one, and so you'll have a weld down this side, and potentially a double lap weld where you weld both sides. So a single lap or double lap where you'll weld both the top and the bottom. You'll have a fillet weld, not a fillet, a fillet weld. You'll have an edge weld, 2 pieces of material here. Right down the center is an edge weld. You have a butt weld, and then you might potentially even have a double butt weld where they're 2 together, weld on the top and then on the bottom. Okay? Key when we're welding is being able to join the material, but get good enough penetration so it won't break, prevent it from breaking or cracking, okay? So what are characteristics of good, solid welds? So you get a crowned surface on a butt weld, so just a slight crown on it, tapers evenly into the base metal. It shows really good penetration, so we're getting even heat on both sides. It is free of gas pockets. What's a gas pocket? What's a gas pocket? Yeah. A bubble under the weld. What else? It's almost like a little hole. It's called porous. You'll sometimes get little porous holes. What's the problem with a porous hole around a weld? That's right, it's going to actually trap moisture in there, okay? So it'll trap moisture in there, where if it's a continuous weld, such as here, you get a continuous weld, it should seal off that material below it, okay? But if it has a hole in it, it's going to allow moisture and corrosion to get in there and actually crack out the material. All right. Uniform in width, hopefully majority of the way it's uniform in width. Ripples are very even. Base material shows no burn due to overheating, okay? A good weld might look like this here. Okay? That's actually an awesome weld, okay? How it's very even, smooth ripples going down. You've got good heat distribution here, okay? All right? So when steel heats up, what happens to the material? It melts. Come on, let's be a little bit more specific. We just got through that whole rundown on welds. I mean, on metal, metallic material.
You talked about the penetration and heat.
Yes. What? You talk about it.
Well, I just remember you talking about how you need to have good penetration, so I assume you're heating up both materials. I know, the little bit I know about welding is, the biggest thing is the thickness of the metal you're going into and the heat distribution.
Okay. Yes, Jedediah?
So when adding heat to the metals, it excites the molecules within it, which allows either softening or hardening, which depending on the types of metals you're combining, will create either stretch fractures or a solid bond between the two materials.
Good. All right, let's go back to aluminum, okay? When I put heat on the outside of aluminum, what happens to the structure of aluminum? Is today Friday? All right, so what happens when we put heat on the outside of aluminum to the core of the aluminum? What happens?
Does it get hard?
we have a alloy aluminum structure, what happens to it when we throw heat to it? It starts to mix. Same thing happens with steel, but at a higher temperature. So here we are throwing 9,000 degree welds, sometimes even hotter, right on top of a piece of steel. Something's going to happen, okay? Something is going to give way. And so that structure actually breaks down. And so if we've carburized the outside of the material, what happens now to that carburized section? Okay, what happens when we carburize it? It gets what? Hard, very hard. Okay? What were you saying, Amanda?
I was just saying it's gonna weaken that.
Exactly. Now I've gotten rid of that carburized outside. Okay? Boom, because I've added so much heat to it. So you're molecularly changing the structure or the compounding of the structures within the material. Okay? Ooh, I have a listening guide for this. Let me open it real quick. I just realized that. It's logged in the case. All right. Ooh, I think this is a fun one because I think I have Smeagol. Have to open it. 144-11, listening guide. Smeagol. All right, Smeagol's open for you. 144-11, listening guide. There it is. All right. Base metal. This is a little tricky here. Base metal shows no burn due to overheating. What is that? I mean, will it show discoloration? Sure. If you're welding, you're going to have some discoloration. But what does it mean by burning? Okay? You're not actually eating away at the other material. You're not just folding it in. Okay? No more oxide than half an inch from the weld, hopefully. Okay? But that will depend on where you're welding. Right here, if I'm welding right here on a T-weld or fillet weld, either one, if you're doing a fillet weld, where's all my heat going to be concentrated at? Right here, right down the center. So my heat is possibly going to be more than half an inch because it's so concentrated in an area. Okay? Where if I'm welding on top here, the heat can go this way. Okay? But it can't on a fillet weld or even a T-weld. Make sense? All right, so good welds. Notice here, this is the top crown. You've got a slight crown on a butt weld. Okay, butt weld, two pieces of metal together. So you got a butt weld here, and it's got a good crown to it with penetration going all the way to the bottom here. Same thing with this one. Okay.
Is that because of the heat distribution that makes it even?
Correct. Yep. Now this gets tricky. How many of you have ever oxygen acetylene weld, or what we call gas welded? How many of you have ever gas welded in here? You got one? Nope, never. Oh, Nathan's afraid to say he has. So he's semi gas weld. Anyone else gas weld? Okay, we got a couple other semi. Anyone who's familiar with gas welding, what is a really difficult thing to do with gas welding? Make it work. Okay. Anyone else familiar with it? Nathan? Anything particularly difficult about gas welding?
Not overheating.
Not overheating. Amanda, you were gonna say something?
Well, isn't gas welding, you have like inert gas, isn't like the shield gas? Or is it, no?
So we're not using like an argon. No, we're using oxygen and acetylene. Acetylene is very flammable and oxygen's adding, making it hotter. I'll put that, it's very elementary, but it's making it hotter, okay? So, unlike like argon, which is TIG and MIG. So, what happens with oxygen and acetylene, you get this cool little torch out here. Alright? Everybody likes fire. You got a cool torch, and we got that torch going. But now all of this is getting hot. Okay? So it's very, very broad heat. Okay? Versus why TIG and MIG is stinking awesome. Okay? Because TIG, if I get sharp enough point, I'm putting that heat right there. Bam! I can get very centralized versus a gas weld where oxygen acetylene's blowing to the moon this way. Everything's getting hot. Okay? And so it's very difficult to get a centralized heat point, okay, with oxygen and acetylene. All right, I agree with just about 80% of these numbers here, okay? So let's go through this. Anyone who's actually welded would look at this and say, ooh, there's a couple problems, okay? So we get a butt weld here. We get a butt weld and we've got a nice crown. Is it going to be 3 to 5 times the thickness of that material? No. I mean, if you had a 1/4 inch and a 1/4 inch and you went 3 to 5 times that thickness, like it'd be bloop. Okay, so some of those numbers don't really work. Okay, I get that. But what they don't want is a huge honking glob popping out the bottom here. Okay? You don't want the metal distorted. You don't want to see it's like, oh yeah, that's a good weld, but the metal just did that. Okay? So we don't want to see huge distortion. On this fillet weld here, you have 1 1/3 to 1.5 thickness here. So you get this thickness, and this is pretty typical. What you don't want to see with a fillet weld is an undercut, where it comes down in here. Okay? Why is that? Randall? Yeah, it's going to be weak, okay? So you want it pretty straight across or it's just slightly contoured. You don't want it undercut. Be real careful with it being undercut. All right. I think this is a picture from your book, this next one here. All right. What are some bad welds here? These are all 4 welds, but what's wrong with them? Okay, let's pick the first one. What's wrong with the first weld? Yeah, splattered everywhere. That's definitely a gas weld for sure. Okay, or it's somebody who just MIG welded and didn't turn the argon on. If you're wondering why the welder is messing up, it's probably you. So you gotta turn the argon, the other little tank on. That's really important. Actually, that's probably majority of the students coming here and they'll be like, something's wrong with the welder. You go in there and you turn the tank on. Oh, okay, thanks. So, splatter or shielding gas probably not turned on. And what happens is there's no crown and it looks like it got abused here. Okay. All right, Bravo. What's wrong with Bravo here? Not deep enough penetration at all. Okay. It looks great, it hides some sins, but did not go all the way to the bottom, okay? What about this one here? This one's getting in the ballpark like, oh, that might be a pretty good weld. What's wrong with that one?
Rough on top.
Rough on top, doesn't have a pretty little crown, okay? It doesn't go very far across, okay? So it's kind of a shallow weld. All right, Delta is definitely a shallow weld. Real nice, smooth. Of course, it's computer generated, so of course it's smooth. But very smooth weld, but nothing there. Okay. Probably probably way too fast, just slapped it down and said, oh, yeah, it's good to go. Okay?
Hey Ryan,
Yes, ma'am.
what if you can't see like the cross view of your weld, and like so you can't actually see how far you penetrated, and because I guess you can have a nice, pretty weld, but it won't penetrate well. How do you know you penetrated well?
Sometimes you won't know. Here, I'll tell you what, I'll pass this around. And if you look at these welds, it's like, man, I got no idea. You know? They're phenomenal welds, but how do I know that this got welded all the way through? I have no idea.
Unless you break it.
Well, then you gotta weld it up.
Let's say if I break it to look at an airworthy weld, it becomes an unairworthy weld.
Makes it easy to decide.
All right, you guys are not helping, you're hurting today. Okay, let's talk about different types of welds, okay? Arc or stick welding, okay, probably one of the most common welds that you can do anywhere in the world, okay? I packed up a Miller stick welder, took it across the pond. That's across the ocean. Across the ocean, and was able to get sticks, able to get actually even cables that we wanted, that we needed, and we could weld on the side of the road. Super cool. Weld just about anywhere in the world. You can get sticks, literally almost every country. Okay. It's about 6,500 degrees at the spot. What's the trick with stick welding? So what? Holding it the right distance. It's really tough to get real centralized with your spark, okay? Because it's still, sometimes it can be kind of wide, okay? Trying to get it to go through. Also, oftentimes it's got to be a pretty clean surface to get a good weld. Now, I used to use DC negative, which is a really good weld. But the old school where you just had an arc weld or AC weld, it had to be a real clean surface, okay? And one fault is that it's also a cooler temp to it too. What were you saying? What were you saying? Somebody saying something?
No, I was thinking, what I've noticed, the hardest part is, just, it's not great for thin material.
Good, it's not great for thin material at all, yep. This is also one that you could use with batteries, okay, when I was talking about, you could literally get a stick, like this, and be able to use them with two 12-volt batteries, run in series as 24 volts, yep. Anyone else? Any other
Ryan,
comments?
are these examples of good welds?
Yeah.
Thank you.
But then I would say, well, according to AC 4313, are they good welds? All right. MIG weld. I will say that as I was leaving the mission field in Ghana in 2021, right after COVID, I started to see the very first MIG welders show up. Pretty cool that it had come a long way to be able to find MIG welders. Now, I realized they were already there, but I'm saying on the local market. Like, you could go down and buy a brand new machine. So, pretty cool that they were having argon available. Now, notice the temperature of MIG. What's the temp? 14,000 degrees. Now, does that mean every time I arc it there, boom, it's 14,000? No. You can control the temperature on a MIG a whole lot easier. So it has the ability up to 14,000 degrees. Okay? What's another benefit, those of you who have ever MIG'd, what's the benefit of MIG? Besides easy. Say what?
They're clean.
It's clean. It's fast. It's super, super, super fast. You can MIG weld probably half the time that you can stick and a third of the time that you can TIG. Okay? Maybe even a fourth of the time that you can TIG. So MIG welding is super fast. All right? But in aviation, we don't use MIG welds. Why is that? why is it uncommon? I can't say we can't totally, but why is it uncommon in aviation? Those of you who've ever MIG weld, why? Why would you think? Let's use a little bit of logic here.
Is it like, or because we're, I mean, it's not necessarily maintenance indoors or outdoors, it's like, I'm not sure. But
Those are all good reasons, but it's actually because when you MIG weld, you can just slap it on there and cover a lot of stuff up. I'm telling you, when we were doing skid loaders, I mean, if it looked bad, we just kept welding. And you could just pile as much weld on there as you want until eventually it's gonna stick. You just turn the temp up, or you don't like it, fine. Just turn it on up until eventually it penetrates it and gets a weld on there that the tree company can't break, okay? This is actually why I wear glasses right here. I was using an auto darkening helmet that a guy had left outside. The morning dew had got inside the auto darkening, and I was welding on a skid loader. Sure enough, boom. That afternoon I couldn't see a thing. So went to the eye doctor, and he's like, well, I can fix it for $5,000 an eye, or you can wear glasses. So for the last 11 years I've worn glasses. So it's pretty serious that we have really good goggles or masks when we're welding, okay? TIG welding, you will have an opportunity to weld TIG here. We have various types of TIG machines. And TIG is an absolute artwork, okay? It takes patience and perseverance. Patience and perseverance. But once you have the art of TIG, you can do just about any type of welding, because you actually have to read the puddle as you're doing it. TIG requires two separate rods. One rod is in the actual head, and then you're going to have a filler rod over here, okay? This one will cause a shock if you touch it to the actual arcing rod. If you touch it right to it, instead of touching it to the material, you could get a really nice little zap, okay? But, for example, TIG weld you use in aviation a lot. Exhaust pipes, or like the beach jet staircase. I re-welded that one. That was a stainless steel staircase. Re-welded it. You'll use two separate because I can centralize my heat. I can get it very pinpointed and get good penetration that way. Okay? 19,000 degrees. And I can also regulate with the pedal. So the whole time you're welding, you're reading your puddle. You can go all the way down with your pedal, get it started, and then backing off. And then based on the flow, you're sitting there just like a gas pedal, where you can control that temperature the whole time you're welding. Versus MIG, guess what? You pull the trigger, it's going on there. Boom. You actually physically have to turn around and turn the machine down while it's welding to be able to see, okay, is it good or is it not? Or you got to stop it, then turn it down. Okay? Versus TIG, you just let up on the pedal. Okay? Make sense? Like a gas pedal. You know? You don't have to, what do? All the way down, hammer down. Get it started right, and then we let off. Okay? Alright, gas welding. Here's gas welding. You got a torch, and it's usually kind of ugly and messy, but FA approved. Okay? So oxygen, we mix oxygen and acetylene. Acetylene is extremely flammable. Oxygen, not flammable. Surprise, surprise. Oxygen is not flammable, but it accelerates a flame. And it's only 5,000 to 6,000 degrees. Problem is, it's not centralized. It's very broad heat. Okay? All right, look at this weld real quick, okay? Welded too rapidly, okay? We have long and pointed ripples. Splattered everywhere, probably didn't have the shielding gas on. Excessive heat, oxidizing flame. What's oxidizing flame? my gas welders, ooh, what's an oxidizing flame? Nobody wants to say. Come on, you know what an oxidizing flame is. What is it?
Is that when it's not a clean flame, it's kind of messy, it's more orange?
Yeah, you potentially added more oxygen than was needed, because remember, oxygen aids the acetylene. So you probably had oxygen too high and not enough acetylene. So it becomes an oxidizing flame. And that will push it down, okay, instead of beating up, making it hot enough, okay? So it's just pushing that weld down. Gas pockets, we could have a potential pocket in here. This one on the right doesn't show any pockets, but you could actually get voids, especially on the edges here, okay? Porosity, slag inclusions, okay? So you might even have little areas that stick out. Looks kind of hideous, okay? Could be something's out of gas. If you're doing a MIG or TIG, it could be that you're out of shielding gas, okay? That's annoying as well. Yes, sir, Dave?
So you're saying, you say it's too much oxygen to acetylene, that ratio?
Yep, and I'll go through that in just a second. I have a kind of a visual picture of it. What happens if the surface is dirty? If you have grease when you're trying to weld. You're like machinery, you're out there trying to weld it, and it's like, just pops everywhere. What do? Turn up the heat, right? Burn it off. But if you want a really good clean weld, grind off that area, and then come back through, get all the paint, all the grease off, come back, and put a good weld on there. Okay. All right. Here we go. So speed is pretty good. Okay. I realize the weld's not perfect. Fine. But look at the area. Look at the width of this weld. Okay. What type of weld is this, possibly? What type of welder is that? Huh? You said MIG, yeah. It is 100% probably MIG, okay? What's the coloration out here? What's that all about? I can't hear you.
It's where the heat is.
Where the heat is, okay? So you can actually tell, look at how wide this one is, okay? We got good heat distance here. We've got pretty even though we have some kind of like puddle or something happen there. Anyway, good, even, smooth weld. Right here, we're just slapping it on there. Boom! You know, speed demon back there, you know, firewall forward, okay? Just slapped it down there. Didn't even care about how even it was. Just get the weld on the metal, okay? Congratulations. All right? And then this one here, they did not like the color of the metal, so they added more to it, okay? And so this one, I didn't show the back of it, but I guarantee you the back of it looked like, you know, the Grand Canyon sticking out the back there where the weld went all the way through it, okay? This is not more of a weld, this is more of a sabotaging, okay? And look how wide the heat went over here. I mean, it's like, we're going to change the structure permanently, okay? That's not really a weld. Just way too slow, destroyed it. All right, David, here you go, buddy. So when we look at the tip, a neutral flame will have just a slight triangular arc there. See that? You have a slight triangular arc. We got an oxidizing flame. We don't have that pretty, it's way too long. We don't have that real pretty covering here, okay? Carburizing flame, it's not smooth. It's too long inside here, okay? Typically, it's going to make it look pretty hideous with a carburizing flame as well, okay? So the neutral flame, you want it somewhere about like this. Nice, smooth, and neutral flame, okay? Yes, sir?
The oxidizing, that's too much oxygen.
Oxygen's too high, yeah.
And then the carburizing is settling.
You nailed it.
Okay.
Got it. Yep.
What are the temperature ranges for these?
I'm not sure. Not sure off the top of my head. It's in your book, but I'm not sure, I can't tell you exactly what it is yet. We'll show you these today in the welding shop, exactly what a oxidizing versus a neutral flame and carburizing flame is, okay? All right, why don't you guys take a break? How about I give you till 5 after?